Okay, now that we've discussed vectors as arrows, we're now going to introduce some coordinates to describe vectors. So you see this vector v in the xy plane, its tail is at the origin, and its tip is at the point 3, 2. Okay, so I could go ahead and describe this vector v in what I'll call the component form, where notice here, since this is a vector, instead of using the parentheses as I do for a point in the xy plane, okay, I'm going to use this angle bracket notation for the vector v, and I call 3 the x component and 2 the y component of the vector v. Okay, now you have to remember this convention that we discussed in the first video that says that a vector is defined by its direction and magnitude only. So in other words, if I take this vector v and I shift it around in a parallel fashion where I don't change its direction and magnitude, these vectors that you see here, in fact, are all the same vector. And what's the thing that unites them? Well, they all have the same direction and magnitude. Or put another way, if I run from the tail to the tip, okay, I have to move horizontally 3 units and vertically 2 units. Okay, so it's really in that sense you want to understand what this 3, 2 in angle brackets is really telling you. Okay, so the vector can have its tail and its tip located anywhere, but as long as I have to run 3 units horizontally and 2 units vertically, okay, that is the vector v. Okay, all right, now let's talk about some vector arithmetic in components. All right, so I have 2 vectors v and w, and I'm going to write them in component form. So for v, I have v1, v2, and for w, I have w1, w2. Now, quick note on notation here. Notice for the vector v, you see that arrow, right? And that's just indicating that this is a vector quantity. But for v1 and v2 on their own, right, these being the x and y components, these are just real numbers, right? These are not vectors themselves. So it's not correct to put arrows over the v1 and the v2. Okay, and likewise for w1 and w2. Okay, so now let's talk about adding 2 vectors in component form. Well, this is really simple. To add v and w in component form, all I do is add their x components and I add their y components. And this vector here, you see on the right, that is the vector sum. Why is that the case? Well, going over to this diagram here, looking at v here, right, so the horizontal component is v1 and the vertical component is v2. So if I apply, right, the convention for summing 2 vectors according to what we've discussed, just working with arrows, I attach the tail of w to the tip of v, and then I form the resultant vector v plus w where I run from the tail of v to the tip of w. Now looking at the components of v plus w, we'll notice for the horizontal component I have to move over v1 and then I have to move over an additional w1. So in other words, I have to run over v1 plus w1 horizontally. And then for the vertical component of the sum, well, I have to move up v2 and then another w2 step there, and that gives me, right, for my vertical component, v2 plus w2. All right, so that's nice, pretty simple. All right, let's look at the difference. Well, again, very simple in components. You just subtract the x components, so v1 minus w1, and then you subtract the y components, v2 minus w2, and that's how you take the difference. And why is that true? Well, right, we said for the difference vector, if you have the 2 vectors situated so their tails coincide like you have in this diagram, the difference v minus w runs from the tip of w to the tip of v. Okay, so for this orange vector, the horizontal component, how much do I have to move horizontally to get from tail to tip for orange? Well, it's going to be the difference in v1 and w1, right? So v1 is this entire length from the origin out here, and then w1 is this length. Their difference is just this gap between w1 and v1. So that's the horizontal component of the difference vector, and likewise for the vertical component. If I take the difference in v2 and w2. That gives me this gap, and I can see that that's the vertical component of the difference. Okay, so not bad there. And then for scalar multiples, very simple. In components, you just scale each component individually. So c, where c is a scalar, times the vector v, well, just distribute c to each component, so you get cv1 and cv2, and that's going to give you the scaled vector. And the reasoning there is very simple, right? If my vector v is here, to scale it by some factor c, that's just going to stretch out both the horizontal and the vertical components, right, by that scalar c, and that's going to give you this scaled vector cv. All right, and then the last thing I'll say here is to compute the magnitude of a vector v in components. This is just the Pythagorean Theorem. Okay, so I can consider this right triangle here. Now the base of this triangle is just the horizontal component of v, so in other words it's v1 that I indicate there in blue, and likewise for the height of the triangle, that's just the vertical component of v, that's v2. And so if I do v1 squared plus v2 squared, I get the hypotenuse squared, and the hypotenuse is just the length of the arrow representing v, and so by definition that's just the magnitude squared, right? So if I take square roots, I get that the magnitude of v is the root of v1 squared plus v2 squared. All right, pretty simple. And now let's go ahead and look at a quick example. So let's say v is the vector 3, 2, and w is the vector -1, 4. Okay, so to form the vector 5v minus 2w, well, scale v by 5. So I'm just, according to this, going to multiply the 3 and the 2 by 5, and that's going to give me 15, 10. Then I'm going to subtract from that 2w. Well, what's 2w? -1 times 2 is -2, and 4 times 2 is 8. Now to subtract these two vectors, as we're seeing down here, you just subtract components, right? So 15 minus a -2, that's 17 for the x component. Then 10 minus 8, that'd be 2 for the y component. All right, not bad. Magnitude of v, well, as we're saying down here, that's going to be the root of the x component squared, so 3 squared, plus the y component squared, that'd be 2 squared. And so that's 9 and 4 is 13 under root. So root of 13, that's the magnitude of this vector v. Okay, great. So now let's press on. Make some space here. And next up, I want to talk about what are called the basis vectors. Okay, so the basis vectors, these are the vectors I and j. Okay, so I, by definition, is the vector whose x component is 1 and whose y component is 0. So you see that right here. So it just points points along, points to the right, and its magnitude is 1. Okay, and j, likewise, well, it points up, right? And its x component is 0 and its y component is 1. And so you see that there. All right, so now what makes these vectors nice? If I give you any vector, say the vector v, who in component form is 3, 2, well, I can build v out of these basis vectors I and j as follows, right? So how much I do I need to construct the horizontal component of the vector v? Well, I need 1i, 2i, 3i's. So I need a total of 3 i's to build the horizontal component of the vector v. How about for the vertical component of v? Well, I need j and then another j, so I need 2 j's. And notice, right, these coefficients, the 3 and the 2 of the vectors I and j, those are simply the x and the y components of the vector v. Okay, so more generally, you want to think of I and j as building block vectors. If I give you any vector v, who in component form is v1, v2, okay, you can write that as v1 times the basis vector I plus v2 times the basis vector j. Now, notationally, you got to be a little careful here. Again, v1 and v2 on their own. Those are just real numbers, right? That's the 3 and the 2 that you see up here in this example. So I don't have arrows over the v1 and the v2, but I and j themselves, those are vectors. And so I do need arrows over there. Okay, now I've been calling v1 the x component and v2 the y component. Well, given, right, this identification we're writing down here, we also oftentimes call v1 the I component. It's the coefficient of I, right, to form the horizontal component of the vector v. And likewise, v2, we will refer to that oftentimes as the j component. All right, now, with that in mind, let's go ahead and look at a quick example. So you have the vector v, right? This is negative 3i plus 2j, and w, that's negative I minus 4j. All right, so let's form the vector 2v minus 5w. Well, this works just the same way as what we had for components, right, given this identification here. So 2v, I'm just going to scale, right, the I component and the j component by 2. That's going to give me negative 6i plus 4j. And then what's 5w? Well, scale the I and the j components of w by 5. And so that'd be minus 5i, and that'd be minus 20j. And now I'm subtracting 5w from 2v. And this is just like combining terms in algebra, right? So I want to gather up all the I terms. So I have negative 6i here, and then a minus a negative 5i. So that's what? Negative 6i plus 5i, that'd be negative I. And then for the j terms, 4j plus 20j, that's 24j. All right, and then how about computing the magnitude of 2v minus 5w? Well, as we said, right, you take the square root of the sum of the squares of the components of the vector. So given that 2v minus 5w is negative I plus 24j, to find its magnitude, you want to take the square root of negative 1 squared plus 24 squared, and that turns out to be the root of 577. All right, great. Well, that's going to do it for this video. We'll look at some more examples in the next video. See you there.